Hi, everyone. I'm going to present our work, Godot, all the benefits of implicit and explicit futures. My name is Kiko. So this talk is going to be about futures, and futures are just a placeholder for possibly not yet computed values. Before I continue, I'm going to explain what do we mean with explicit and explicit futures, the problems that we find, and our solution which kind of solves them. So I'm going to explain this with an example. In this case, we're going to have some kind of client, which is an actor, and it's going to send a message to a proxy server. And the proxy server is just going to try to find some kind of idle printer and delegate the work so that the printer does the actual printing. The code could look something similar to this. And in this case, the client goes and sends a message to the proxy. Because he's sending a message, it's going to create a future. And the future in this case is kind of this magic ball. We go and send the message. Afterwards, what happens is the proxy tries to find some kind of idle worker. And after it finds the actual printer, it's going to send a message to the printer so that it does the printing. Because if sending a message again, it's going to create a new future. And it does the sending of a message. Finally, because there's nothing more to run in this case on the proxy, this future gets fulfilled with this other future, right? And now we need to see how the printer actually fulfills this other future. So in this case, the printer goes, does the printing of the job, and says, hey, I have finished, so I'm going to say that everything went well. It goes and puts the value inside that future. So now, if the client wants to get access to the final result, it needs to go through two double blocking operations. The first one which says, I'm going to check the result of the future, and we know that the result of this future is actually this other future. And now you need to do again another operation on the future so that you go and fetch the actual value which was the result true. So explicit, in this case, refers to the typing, where the future type is available to the developer. Ludovic Henrio recently identified that this kind of futures are usually tied to control-flow synchronization, where we understand as control-flow as having access to all the intermediate steps. So this kind of future of a future, right? We can access those intermediate steps. Now with explicit futures come explicit problems. The first problem that we identified is the type proliferation problem. And this is something that happens statically. It basically means that because we're creating this kind of nest of futures, the code is going to mirror the communication structure, right? And this leads to inflexible code. We also identified the future proliferation problem, and this one refers more at the runtime. So whenever we create this kind of nest of futures, we know that at runtime, we're going to have to deal with n nested operation of futures, such that a nest of futures of depth n is going to add n additional operations. Now we're going to turn into implicit futures. Implicit futures are pretty much basically the same as explicit futures, except that the future type is not available to the developer. So the code is pretty much exactly the same as before, except that I have removed the future type over there. So what happens is the client is going to send again a message to the proxy. When it sends the message, it's something that's not visible to the developer, but it's going to create at runtime a new future. It goes and sends a message. Now the printer does the same thing as before. Try to look for some kind of idle worker, finds it, and sends a new message to the actual printer. So it creates again a new future. Overall, we can see that the future type is not visible to the developer, but this is happening at runtime. Now, as before, this future basically gets fulfilled by this other one. And then we see as well that the return of the printer is the one that goes into this future. So again, at runtime, we're going to have to deal with futures of futures. This is not visible to the developer, so it's not something that you can try to do this kind of double blocking or something. So whenever the developer goes and tries to use the response variable value, it's going to actually perform this kind of double blocking at runtime. So implicit futures, in this case, refers to not having access to the future type. And Ludovic Henrio identified that implicit futures have been so far linked to data flow synchronization, where we understand data flow synchronization as losing or basically not caring about the intermediate steps, just going from this future and you get, or not in the future, from this variable and getting the result automatically. But you don't have access to the intermediate steps, which doesn't allow you possibly to encode some kind of communication patterns when you want to see that something has been scheduled and then something has been run or similar. So with implicit futures come the implicit problems. This is at runtime, the one that we identified before, the future proliferation problem. In this case, statically, we only know that there's going to be some kind of Boolean. And at runtime, because we're creating this kind of nested depth of futures, we're going to have to block possibly twice on the future. We also identified the fulfillment observation problem. And this is what I mentioned briefly before. Because there's no future type, there's no way to check whether a job has been scheduled and then whether the job has been run and so on. Right? So this is something that it is not possible to do with implicit futures. Now, this is the problematization matrix. At the top, we have the problems. And here on the left to you, we have this kind of dichotomy between control flow, data flow, and explicit and implicit futures. Just to make it simpler to understand, control flow explicit is where you have access to the intermediate steps and you have access to the future type. So this could be Java. Data flow and implicit could be JavaScript. You don't have access in this case to the type, and whenever you try to access the value, you just go the future value, then you just get the end result, not the intermediate steps. Control flow implicit will be the kind of future in which the future type is not available to the developer, but somehow you want to access the intermediate steps. This has not been studied as far as we know by anyone. And then data flow explicit futures would be the futures that are typed, so available to the developer, and where you can have this kind of data flow computations where you just want to get the end result without having access to the intermediate steps. We're going to work on this space, and we built on top of work by Ludovic Henrio with data flow explicit futures and previous work from ours. I do not have time to cover the previous work, but I will mention when we have taken the inspiration from this work. So the contribution of this paper is the creation or the integration of data flow and control flow explicit futures in the calculus. And in the artifact, we have an implementation in Scala. We also take inspiration from runtime optimizations using this kind of forward related work that I'm going to explain in a bit. We have encodings of control flow futures in terms of data flow and vice versa. So this means if you are using Java, we're going to tell you basically how you can encode data flow futures. And if you are using some other kind of language in which you already have the data flow futures, we tell you how to add the control flow futures. And there are some other goodies in the paper. For this presentation, I'm going to show an example of what do I mean with this kind of data flow futures mixed together with control flow futures. I'm going to show as well just bits of the calculus so that we can see how we are solving those problems. Just to start with example, we saw that this is the control flow future, right, in which the client sends a message to the proxy. The proxy says, hey, you are the one who are idle, so go and do the printing. And if somehow we want to add capabilities for the printer to say, yeah, I was really not idle, so continue until I find some other printer that actually does the printing. This is what's going to happen. We're going to create many intermediate futures, and now you need to go with this kind of cascading thing of fulfilling. So if you are here and you want to get the end result, all of this is going to be mimicked at the type level. With our work, we introduce a new type, which is called flow, for data flow futures. And what happens in this case is we're going to send a message. So we create this kind of data flow future. And now, if what happens is that we continue kind of finishing by spawning new computations or delegating the work, we just don't need to care about creating any more intermediate future. And we basically say, you know what, you are really the one in charge of fulfilling this initial future. And we do not need to create intermediate ones. So this is a runtime optimization that we can do in our work. Because we have access as well to control flow futures, we could say that we're interested in first maybe creating or sending a message, creating a control flow future, and then saying, I don't care anymore about whatever happens in the middle, the intermediate steps. I know I can check whether the job has been scheduled, and then I'm only interested in the final result. So again, we don't need to go through all these intermediate steps. We just go and delegate the work and say, the printer is the one that's going to fulfill this future. Now, in terms of the core calculus, we're going to use tasks because it was easier for the proofs. And this is just a concurrent-based calculus on top of system F. As new expressions, we have the spawning of a data flow future, the blocking operation to block on the future until there is a value, and some other ones that we're going to see a bit later. Regarding the typing rules, this is all there is for the paper, so it's pretty simple. And we're going to focus, it is simple. I know someone laughing, but it is simple. And we're going to focus specifically on this rule, because it's the one that is interesting for solving one of the problems. So we're going to see how this rule solves the type proliferation problem. And just as a reminder, the type proliferation problem basically says that the type is going to mirror the communication structure, so you're going to end up with futures of futures, right? We read this as, given some kind of environment, whenever I want to spawn a new computation, I'm going to get back a data flow future with some kind of arrow. This kind of down arrow is just a type level application. And the only thing it does is, if this kind of tau, for some reason, is another flow, data flow future, you are going to compress it. So it's just a type normalization thing. And this is really what I meant, right? If we end up with some kind of flow of a flow, then we're going to compress it. And now you don't have the flow of a flow. With this, we solve the type proliferation problem statically, but we still don't know how to fix the runtime issue, right? So the future proliferation problem. So statically, we know that now data flow futures are going to be compressed. So good. Now, we look at the runtime semantics. Again, this is all there is. There's nothing more. Plus 2 optimizations. I'm going to show one of them. Again, we focus on the rule of spawning a computation. In this case, what this rule says, if I have a task that after running this thing fulfills the data flow future G, and I want to spawn a new task, then I create a new data flow future, so that thing over there. I create a new task that after running this expression fulfills this data flow future. And the original task gets immediately the data flow future that I created. As it is right now, this would be the semantics of Java. So this is nothing new. So what we introduce in this case is an optimization. And we say we're going to identify now tasks with some kind of super index so that we know that 2 tasks are actually different. And we say whenever one task finishes by spawning a new computation, what we do is we create a new task, but we delegate the work of fulfilling the future to the new computation. So we're not anymore creating this kind of new data flow future. We're delegating the work of fulfilling the future that you had access to. So with this, we remove basically the creation of a nest of futures at runtime. This also allows us to run asynchronous recursive computations in constant space with respect to the creation of futures. Okay. Finally, we go to the encodings, where we're going to see how we solve the fulfillment observation problem, which is that we do not have access to the intermediate steps. So far, in the current calculus, you don't know how to have access to the intermediate steps because it's a data flow computation. So we introduce, in this case, an encoding, and we say that whenever you see some kind of future of tau, this is actually an encoding for a box combinator, which is an algebraic data type in the implementation of a flow type. So you don't need to create two built-in types or anything. This is just an encoding, which is much nicer, right? Now, if I want to work on control flow futures, so Java futures, I'm going to express that with the blocking operation to get a value from the future is going to be get. And it's again an encoding in terms of data flow combinators. We're going to have this kind of get star, which blocks on data flow futures, and some kind of new thing that I'm going to explain when we see the async. Now, the future type is typed as you would expect. Whenever I want to get the value out of some E, which is a future, then I get the value out of it. And this match really nicely with the async operation. So spawning now a control flow future, so your Java future, is basically putting this kind of box there, and then a control flow computation. If we try to match, or we take this thing and plug it just right there, it would be unbox and box cancel each other, and then we're just working in terms of the data flow combinators or operations. So with this, we have access to the intermediate steps, and we can encode control flow futures in terms of data flow. So now you can stop and check whether some kind of job has been scheduled in the meter. Now, there are more goodies in the paper, as I said. We have the encodings of data flow futures in terms of control flow futures, but we also have the opposite. We tell you, if you are from Java, we tell you how to create the data flow computations. There are implementation guidelines. We have the artifact, a formalization of both calculi. So again, the one that you start with, Java, and then the one that you start with the other data flow future language, how you can add them. We also have some other things that I'm not able to cover in 70 minutes. So to sum up, we have identified problems in implicit and explicit futures, a system that integrates control and data flow futures, the formal semantics, the encodings. Check out our poster. I will be there explaining more stuff if you're interested. And the most important part, possibly, I'm looking for a postdoc for August 2020, so there's still some time to get funding if you're interested in this. Thank you.
So I think we just have time for one question. Could I ask Daniel to come and start setting up his laptop? Thank you. Any questions?
Yeah, for sure.
So, here, first row. Okay. So the optimization you do to contact back to the original future, you basically are assuming that all machines know each other.
All machines, yeah, because it's an actual language, right? Then you need to have the identity, right?
Yeah.
So you know to whom you're talking to. Yeah.
So you assume that they know each other and there are no partitions. If you have like the three machines on the top isolated from the other ones, the optimization wouldn't work there.
No, the optimization works. I'm not sure I understand the question.
So because you show different machines.
Yeah.
And so there could be a partition. So there could be a network failure and three machines are isolated from the rest.
Yeah.
But the optimization basically resolves the first future, but you might not be able to contact that one.
Well,
directly. Yeah.
So yes, I can give you the details because it's kind of related to previous work, but you don't know how to contact that. Internally, the implementation could be relying on promises, and that's why at runtime you kind of carry the promise around, and you know that the one that finishes at the end is the one that needs to fulfill the promise. So that's why you don't need to do that. I can explain the details later if you want.
Great, thanks very much. Let's thank our speaker again.